Understand dot product, the heart of neural nets. By the end, you will see dot as a simple weighted sum, convert it to cosine similarity to remove length bias, and build a tiny neuron that classifies a query. I'm Professor Pi, teaching AI foundations with Python from basics to advanced. Dot product intuition matters because it directly measures alignment between signals. In neural nets, it optimizes activation alignment, which drives learning. The main trade-off is magnitude versus direction. A large vector can dominate a raw dot, so we sometimes pay a small compute cost to normalize. At production scale, this choice changes ranking quality and latency in measurable ways. At a high level, dot product shines when you want fast, linear relevance. It breaks when magnitude is irrelevant and direction matters. We will show both raw dot and cosine, and then use them to rank tiny document vectors and to build a one-neuron classifier. Now we start the hands-on walkthrough. This snippet computes a simple dot product as a weighted sum. This snippet shows the core idea. Multiply each component of one vector by the corresponding component of another, and then add those products. Spoken plainly, the result is a single number that grows when vectors point in the same general direction and when their values are large. Use this when you want raw signal strength or when magnitudes carry meaning. If you increase vector magnitudes, the dot grows proportionally, which speeds separation but introduces magnitude bias. If you scale inputs down, the dot shrinks and lessens that bias. Now, we move to remove magnitude effects and focus on direction. This snippet turns the dot product into a cosine similarity. This snippet normalizes each vector to unit length before computing the dot, so the number now measures pure angle between vectors rather than combined size and alignment. In practice, this trades a tiny amount of extra computation for a more meaningful similarity in many tasks. When you increase numerical precision or add vector smoothing, the cosine becomes more stable. If you normalize noisy small vectors, you can amplify noise. So consider adding a small floor to norms. Cosine is ideal when you care about how two signals point, not how big they are. Next, we use dot to rank a tiny collection of document vectors by relevance. This snippet ranks tiny document vectors by query relevance using dot. This snippet computes dot scores between a query vector and each document vector, sorts those scores, and returns the top matches. It shows how raw dot ranking prefers documents that both point in a similar direction and have larger magnitudes. If you change the number of top results returned, you alter recall and precision trade-offs. If you scale up the corpus, the computation cost grows linearly, so you may later add indexing. This simple ranker is fast for small collections and is a clear baseline for comparisons. Now we switch the ranking metric to remove that magnitude bias. This snippet switches to cosine ranking to remove magnitude bias. This snippet first normalizes query and document vectors and then ranks by their cosine similarity. So the output favors directional match alone. Changing normalization or adding a small epsilon to avoid division by zero affects stability on tiny vectors. If you move from dot to cosine, you will often improve relevance in retrieval tasks where documents vary in length. The trade-off is a small compute overhead and potential noise amplification for low-magnitude vectors. Use this when you want fair comparison across different size documents. Finally, we build a tiny neuron with bias and a sigmoid to classify the query. This snippet builds a tiny neuron with bias and sigmoid to classify. This snippet takes a dot between inputs and weights, adds a bias term, and passes the result through a sigmoid nonlinearity to produce a probability-like output. Changing the bias shifts the decision boundary, and changing weight magnitudes scales sensitivity to input features. If you increase weight magnitudes, the neuron becomes more confident and steeper in classification, which can help separable data but hurt generalization. This simple neuron is the exact mechanism at the core of larger networks, where many such units are stacked and trained together. Recap! Dot product is a weighted sum that measures alignment and magnitude. Use raw dot for speed and when magnitude matters. Use cosine when direction alone matters. One caveat, normalization can amplify noise in low magnitude vectors. Next step, scale this exact pipeline to a larger collection and measure performance. Swap raw search for an approximate nearest neighbor index and compare dot versus cosine ranking on timing and accuracy. Tuning the index parameters to balance speed and recall. If AI Foundations in Python help you, subscribe and watch the AI Foundations videos.